9 is on mathematical modeling and optimization. So we're going to be dealing with optimization, which means finding the maxes and mins of functions. Do we know how to find the max and min of a function? How do we find the max and min if I gave you a curve? Yeah, so if I had an f of x, I would find when my first derivative was equal to 0 or where it was undefined. And then I did my number line. I would show that it goes up and then down for a maximum, or down and then up for a minimum, right? For f prime is positive and then f prime is negative for a max. You guys remember all this? Yeah, we know how to do this. We've been doing this. So what makes this section different? Oh, it's story problems. Your fave. So we're going to deal with story problems pretty much for the rest of chapter 4 or whatever we're on chapter 4. So yeah, we're going to have a lot of story problems. All right, so it says, what are the most common applications of calculus involves optimizing a solution? So in other words, finding the largest or smallest of some quantity that will fulfill a need. So I found lots of examples, and I'm showing them. So it says typical solutions are find the route which will minimize the time it takes to get somewhere. Build a structure using the least amount of material. Build a structure costing the least amount of money. Build a yard enclosing the most amount of space. Find the least medication one should take to help a medical problem, and find the most a business should charge for an item in order to make the most amount of money. Does this make sense? These are maximizing and minimizing. So in order to do this, we need to first understand the problem. So what are the knowns? What are the unknowns? We're going to draw a picture, and we're going to use variables that make sense. So like A for area, L for length, W for width, right? And we're going to decide what's being maximized or minimized. So if it says maximize the cost, then I'm probably going to have a C in my equation, and I'm going to find C prime. Does this make sense? Okay, so it says write an equation. So write an equation using this variable to be maximized or minimized. Make sure it's in terms of one variable. So if we're minimizing an area, we don't want area to look like length times width. We want area to only be in terms of length or only be in terms of width before we take the derivative. Otherwise, we're doing implicit differentiation, and it's going to get a little crazy. Okay, so we're going to try to get it to a single variable.
Oh, so like saying like if you have like width is 1x but length is 3x.
Yeah, something like that. And then find the absolute max or min, and don't forget that you might have endpoints. So sometimes the minimum volume for a box of cereal is to not have a volume at all. Does that make sense?
So
Because it's nothing. Yeah, exactly. So number 1, so it says you have 400 feet of fencing with which to enclose 3 rectangular spaces next to a barn wall. So we are not going to put the fence along the wall. That's weird. Okay, so we're going to have our fence going around, and we're going to have 3 separate like pens. Okay, and so if this distance is x, then the distance, every single vertical distance is also x, right? So we're going to have x, x, and x there. Okay, and our goal is to try to get everything in terms of one variable, but sometimes we introduce other variables. So I'm going to call this y for now. And I'm going to think about the things I have. So it says I have 400 feet of fencing. So imagine I'm taking my fence material. And how am I creating the 400 feet? I have x plus x plus x plus x plus y. Does it make sense? So I have 4x plus y equals 400. Is this what I'm trying to maximize or minimize? Am I trying to maximize the amount of fencing? No. So in the problem it says find the largest area. Okay, that means that this equation is what I would call a secondary equation. It's not our main equation that we're trying to take the derivative of. It's just a useful equation in order to get it in a single variable. So the primary equation, the one we're trying to maximize or minimize, has to do with the largest area. So how do I write the area? Well, the area of this whole The area of this whole piece is x times y, right? You could get fancy and you could say 1/3 y times x plus 1/3 y times, that's crazy though. We're not going to do that because it ends up being x times y, right, when you add them all together. So we're just going to say x times y. But we want a to equal, and then on the right side, only one variable. Okay, so it's really 2 variables, a and then another variable. Okay, so how can I fix that? Yeah, we just substitute in, right? So we're going to take y, and we're going to be like, well, y is really 400 minus 4x. And we're going to substitute it in right there. So we're going to have a equals x times 400 minus 4x. So I get a equals 400x minus 4x squared. So a prime then is going to be 400 minus 8x. Because I'm trying to maximize. I'm trying to find the maximum for this area. So imagine this is some kind of curve. Tell me what the shape this curve is. It's a parabola. It's a downwards parabola. Doesn't a downwards parabola have a maximum? Yeah, so you guys did things like this in pre-calc and algebra 2. You could just use your calculator to find the maximum. Or we did negative b over 2a. That is calculus. That's what we're doing. We're finding the derivative. Remember I've told you that before? Of ax squared plus bx plus c. When you find its derivative, you get 2ax plus b. And when you set it equal to 0, that's where we get the negative b over 2a. Right, that's calculus. Do you guys see that? Okay, that's what we're going to do here. We're just going to do the calculus steps. So we're going to say, well, our derivative is equal to 0 at what x value? 50. And then how do we know that that's a maximum versus a minimum? Yeah, we want to make sure that on both sides, right, if I have 50 here, was I going up and then going down? So was the a prime, was it positive and then a prime was negative, right? Which means a, the area, was increasing and then decreasing. Yeah, it was. So if you plug in like 0 into the derivative, I get 400 minus 0, right? Positive. If I plug in something bigger than 50, like 100, 400 minus 800 is negative. Okay, remember the AP graders don't grade that, so we're going to do, everybody always whines and complains. They're like, oh, I don't want to write out this step. Okay, it takes 3 seconds to write this. So you're going to say a prime is greater than 0 on negative infinity to 50. A prime is less than 0 on 50 to infinity. That's all you have to write. Please, the AP graders. Yes. All right, and then always look to see what you were trying to find. So sometimes it will say dimensions, right? Sometimes it will say find the area. What did it say? It said find the largest area. Is x equals 50 the largest area? No, that's like one of the dimensions, right? That's this distance here. So how do I find the largest area? Go back to your area equation, right? So let's use this one. So my area is going to be 50 times 400 minus 4 times 50. So I get 50 times 200, right? So I think I get 10,000 square feet. Good? All right, so this is kind of how most of them are. Sometimes we don't have secondary equations, which is totally fine. It's easier when there's not. Okay. So let's try the next one. So a square sheet of cardboard. Don't you love these problems? Haven't you seen these in Algebra 2 and Pre-Calc and all those classes? In my Algebra 2 class, I always take a piece of paper and then I cut out little corners and I fold up the flaps. Have you seen me do that before? Yeah, so some of you guys have. Do you guys understand what's happening in this problem? Yeah, so imagine these little corners are cut out. So when you cut out these corners, imagine this is my scissors or my fold line. So if I'm folding on these dotted lines, I end up getting like a little shallow box, like a gift box or something, right? Does this make sense? So originally this distance was 18 inches, and this distance was also 18 inches. But now that we've cut out those little squares, we don't know what size they are, so we put x by x. And we're cutting that out of every single corner. So now this blue fold line isn't 18 inches. How much is it? Yeah, 18 minus 2x. So that's like one of these two distances. And then this one also, 18 minus 2x. And so now when I have those little flaps on the side and I folded it up, how high, so imagine I'm folding it up on the screen, how high is it coming up off the page? X, right? Does that make sense? So that's going to be the height right here, x. So we create a volume equation. So we have the volume is equal to 18 minus 2x times 18 minus 2x times x. So I gave questions like this to my pre-calc class, and I asked them to find a maximum using a calculator. Okay, you end up getting an x cubed equation if you did multiply it out. why would you multiply it out if you have your calculator? Just leave it, right? And then you would find that. Okay. Usually this one that's over here ends up being something that's like usually like 9 or something, where it's too big. So you guys see if you had a side that's 18 inches and you're cutting along the side. So we'll show that in a second. All right, so sadly, let's say we don't have our calculator. Oh, yeah, and yours is broken. In a lot of college classes, you guys know you're not allowed to use calculators anymore in almost every single math class in college. Yeah, even like Calc 3, they don't let you use a calculator. Because a lot of calculators can store information and they don't want to clear calculators every single time. It's kind of dumb. But, you know, in real life, you actually use calculators, so who knows? Yeah. There's kind of a disconnect with what's happening in college and what's happening in high school, so it's a little frustrating sometimes. All right, so anyway, so I get 4x cubed minus 72x squared plus 324x. So when I multiply that out, so that's my volume equation. So I FOILed it out to make it easier to take a derivative because I didn't want to do product rule with the product rule inside the product rule. Okay. So I do v prime equals 12x squared minus 144x plus 324. And 12 goes into all of those. So I get x squared minus 12x. Do you guys know 324 divided by 12? Nope, bigger. 27. It is 3 times 9. Did my Sycamore students know 18 times 18? Did you guys know that? Thanks, Mr. T. Did you know 18 times 18? You did know it, didn't you? Because he makes you memorize it up to 20, right? Actually, some of them have to memorize it up to 25. Yeah. All right, so we get x equals 9 and x equals 3. Yeah. All right, so definitely can't be 0, right? We're gonna consider when x is 0 as well, but it's not gonna be like -1, -2. I can't cut out a negative distance. So I have 3, and then I have this biggest that it can possibly be is 9. Okay, so let's think about what 9 is. So I got this square piece of 18 by 18, and I decide I'm going to cut out 9 inches this way and 9 inches this way. Do I have a volume? No, I have like an envelope, right? There's no thickness. I actually don't have anything. So there's nothing there. I don't know how that's possibly working. So 9 doesn't work. It's out. So now we just got to plug into v prime and make sure that we're trying to get the maximum, right? So we want v prime to be positive and then negative. So that means the volume is increasing and then decreasing, right? So if I plug in like 1 into here, I get 12 times negative is positive. And if I try 4, I get 12 times negative times positive is a negative, right? And remember, they don't grade that, so you would have to write v prime is greater than 0 on 0 to 3. V prime is less than 0 on 3 to 9. So we would say there is a max when I cut out a 3 by 3 square. So the question is, find the dimensions of the box with the maximum area. So our dimensions. Dimensions just means length times width times height, right? So if I plug in the box with the maximum volume, did I say area? Okay. So our dimensions are going to be, if I plug in 3, I get 18 minus 2 times 3, which is 18 minus 6, so 12. So I have 12 inches by 12 inches by 3 inches. Okay, and if it asked for the maximum volume, did I ask for it? No, I didn't ask for it. But you would just multiply those together, right? I know, crazy. All right, so those are our dimensions.
So like in this wording though, it says like find the dimensions of the box with the maximum volume. Like, so that's just read by find the dimensions while plugging in the maximum volume and not solving for it. What if like it did mean
Dimension just means length times width times height. That's all you gotta give.
Well, like what if it did mean for you to solve it, but you misread it?
Well, if you're not sure, then just write off to the side volume equals 432 or whatever. What is that? What it is? 432 cubic inches. Just write it somewhere, just in case. All right. So the next one looks so easy, doesn't it? It says find the point on the parabola y equals 9 minus x squared closest to the point 3, 9. It's not. These are like the hardest ones. So we're going to draw it out. We're going to think about it. So if I have 9 minus x squared, it's a downwards parabola. Y-intercept is what?
0 for 9.
Mm-hmm. I don't know why I gave that so much there. All right, and then x-intercepts? -3 and 3, right? So we have a downwards parabola. And we want a point that's along that parabola that's closest to the point 3, 9. So 3, 9 is hanging out there in space. And if we want to know the point that is closest to that, it's a little weird. Okay, so let's think back to like geometry. Let's say I decide that the point's right here. Don't draw this. Okay, is there a point that's closer along the parabola to that? Yeah, it would be like right here. Yeah, it's always perpendicular. Perpendicular to what? The tangent line.
It's the normal line.
Yeah, it's the normal line. So you could probably use what we've learned before with tangent lines and normal lines and find an equation of a line that's tangent or normal, I guess normal to that curve, and try to figure it out that way. It's probably a lot faster, but let's use the optimization stuff. Okay, it kind of makes sense because if you're thinking of like a right triangle, this is a hypotenuse, which is always bigger than this distance, right? That's the best way to think about it. So we're trying to find the curve or the point that is right around here where it creates that 90-degree angle. Okay, so we have the point 3, 9, but we have another point there, but we don't know the coordinates. So I could call it x, y, or I can call it x, what if I wanted only in terms of x? Instead of calling it x, y? No. X, 9 minus x squared. Isn't it on that curve? Right? Does that make sense? And what are we trying to minimize? Yep. Minimize distance. So we're probably going to have to use what important formula? The distance formula, which you all love so much. So it looks like that. It is, because you take the derivative of something that involves a square root, it gets a little tricky. All right, so our distance then is going to be, let's call this our x2, y2. So it's going to be the square root of x minus 3 squared plus 9 minus x squared minus 9 squared. So then people are like, oh, those 9s cancel. Yeah, it's still annoying. So I'm going to go ahead and FOIL it out just so it's going to be easier to put in my calculator. So I'm going to have x squared minus 6x plus 9 plus, notice how this ends up being like negative x squared squared. So I'm going to have plus x to the 4th. You with me? Okay, and then I'm going to take the derivative, which is really all this junk raised to the 1/2, which means my derivative is 1/2, all that stuff in the middle, raised to the negative 1/2 times 2x minus 6x plus 4x cubed. Yeah, Ashley.
Wouldn't it just be -6?
Oh, yeah, minus 6, thank you. I was moving on. Minus 6, thank you. Thank you for letting her have that, speedsters. All right, so here we go. So on the bottom, I have a square root because it's the negative 1/2 power, right? And really, I could do something with this too, and notice how these are all divisible by 2. If you guys want to divide by 2, you can. If you didn't want to, just leave the 2. That's fine. It doesn't matter. Okay. So it gets a little bit weird. Okay, in order to find possibilities for maxes and mins, what do I need to do? I need to set d prime equal to 0, and then also find where it's undefined. So if I set this equal to 0, it's a little tricky. Like, how do you solve that? You could use rational roots theorem if you didn't have your calculator. I will let you use your calculator. So we're going to go to where we plug that in for y equals. So if you put 2x minus 6 plus 4x cubed, you guys don't have to do it, just kind of pay attention up here. So I think we're running out of time. And I hit graph, I get a cubic function, and it has a certain x-intercept. It is what you think it is. It's 1. And you can check if you plug in 1, what do you guys get? 2 minus 6 plus 4. See how it's 1? If you did a rational roots theorem and tried synthetic division, 1 would work, right? Does that make sense? And you can also do second trace and then find the 0 on your calculator. So left bound, right bound, all of that. So we get 1 there. And then when we set this equal to 0, we end up getting none. So there's no answer there. So our only critical value ends up being 1. And you can check, it does go down and then up for a d prime. So that is a minimum distance. So the question said, find the point, right? Find the point on the parabola closest to the point 3, 9. So what point do we have in the end? Yeah, 1, 8, because you plug into the original parabola equation, 9 minus x squared. Does that make sense? Do you guys get that? Okay, so I don't remember how much. We got like 5 minutes. Let's look kind of at the next one. So let me set this one up for you guys. So it says we want to construct a box whose base length is 3 times the width. And the material used for the box on the top and bottom is $10 per square foot, and on the right and left and front and back it's $6 per square foot. So this happens sometimes. Sometimes you'll see like boxes where it's like plastic along the sides, but then like glass on the top and bottom, or wood along the sides, like a shadow box or something. So we have some kind of box like that. So it says if the box must have a volume of 50 cubic feet, determine the dimensions that will minimize the cost to build the box. So we want to know the cost, and we want to find like C and then C prime. Make sense? Okay, so the base length is 3 times the base width. So I'm going to call this 3W and W along the bottom. But I don't know anything about the height. So what would be a good variable to use for height? H. Perfect. So I'm not finding the volume of the box necessarily, but I'm finding the cost of the box. So our cost is going to be C. And the top and the bottom cost $10 per square feet. So let's talk about the top and the bottom. This is W by 3W. That's the area, right? How do I work in this $10? Yeah, it's going to be like 10 times that area. Do we understand why that works? Because we'd have like 3W squared, which would be in units of feet squared, and then we multiply by our dollars per feet squared. Do you guys see how those feet squareds will like go away? This is going to be in dollars. This is how like dimensional analysis, the things you do in like, what do you call it, stoichiometry, and chemistry works. So we're going to take our cost for the top, which is 10, and we're going to multiply by the area of the top, which is 3W squared. That's just the top of the box. That's how much the top costs. What about the bottom? Another one, right? So I'm going to do times 2. So I'm going to say and bottom. I feel like it's like Sesame Street. All right, how about the right and the left side? W times H. What's it cost? 6. Top or right and left times 2. So that's the right and left. Does that make sense how we're setting this up? I lost you in the last 5 minutes, didn't I? All right, how about the front and the back? Tell me the area of the front side. 3W times H, right? What's it costing per square foot? 6. So I'm going to have 3W times H times 6 for the dollars, right? And then I also have not just the front, but also the back, so times 2. Oops, this is a plus. Front, back. So this works out to be 60W squared plus 12WH plus 36WH, which is 60W squared plus 48WH. And what is our issue? Why can I not take the derivative?
Two variables.
Yeah, there's two variables. I have W and I also have H. So I go and I look for a secondary equation. Do you see a secondary equation? Yeah, it says the volume is 50 cubic feet. So if our volume is 50 cubic feet, that means we have 50 equals 3W times W times H. Yeah, kind of a weird way to say it, but yeah. 3W squared under 50. Yes, so 50 divided by 3W squared. And that's what we're going to replace here, and then we're going to take the derivative from that. Does that make sense? Do you guys see how it works? So we'll pause on that. Remind me that's where I left off when we do this tomorrow.